to our peaceful journey across the scattered volcanic emeralds of the Pacific Ocean, where the Galápagos Islands drift in eternal isolation 1,000 kilometers, or 620 miles, west of the South American coast, creating a natural laboratory where evolution unfolds with the patient precision of geological time. As you settle into comfort this evening, allow your mind to float gently across these 21 major islands and dozens of smaller islets, each one a volcanic monument to the Earth's internal fires, where giant tortoises move with ancient deliberation across lava fields that cooled from molten rock over thousands of years. The Galápagos archipelago spans approximately 8,010 square kilometers, or 3,090 square miles of land, scattered across 45,000 square kilometers, or 17,400 square miles of ocean, positioned precisely on the equator, where the warm waters of the Pacific create conditions for the remarkable biological diversity that inspired Charles Darwin's understanding of natural selection. I wonder where you might be listening from tonight, what part of our world you call home, and what time your clock shows as these words reach you across the vast distances that separate us all. Perhaps you might share that gentle information with us in the comments below, creating our own peaceful archipelago of listeners scattered like islands across the digital ocean. And if you find that these island wanderings bring you the rest you seek, consider subscribing to join us on future explorations of Earth's most isolated yet magnificent landscapes. The Galápagos Islands rest atop the Galápagos hotspot, a stationary plume of superheated rock that rises from deep within the Earth's mantle, creating volcanic islands as the Nazca Plate moves eastward at approximately 5 centimeters or 2 inches per year. This geological conveyor belt has been operating for millions of years, with the oldest islands in the east gradually moving away from the hotspot, while new volcanic activity continues to build the younger western islands. The easternmost islands, including San Cristobal and Hispaniola, show ages of 3 to 4 million years, their volcanic cones weathered and eroded by countless centuries of wind and rain, while the westernmost islands, Isabella and Fernandina, contain active volcanoes that continue to add new land through periodic eruptions that may occur every few years or decades. Isabella Island, the largest in the archipelago, covers 4,640 square kilometers, or 1,790 square miles, and was formed by the merger of 6 separate shield volcanoes that grew from the ocean floor over hundreds of thousands of years. These massive volcanic structures rise from ocean depths exceeding 3,000 meters, or 9,840 feet, making them among the tallest mountains on Earth when measured from their submarine base to their highest peaks. Wolf Volcano, the highest point in the Galápagos, reaches 1,707 meters, or 5,600 feet above sea level. Its broad, gently sloping flanks characteristic of shield volcanoes built from thousands of fluid lava flows that spread outward from central vents over vast periods of time. The volcanic activity that built the Galápagos Islands follows predictable patterns governed by the physics of magma formation and ascent through the Earth's crust. As the mantle plume rises from depths exceeding 2,900 kilometers or 1,800 miles below the surface, it undergoes decompression melting that generates basaltic magma with temperatures approaching 1,200 degrees Celsius or 2,190 degrees Fahrenheit. This magma accumulates in chambers several kilometers beneath the surface before erupting through fissures and vents that may remain active for decades or centuries before shifting to new locations. As the overlying plate continues its eastward movement, the lava flows that build these volcanic islands consist primarily of basalt, a dark, dense rock that forms when iron-rich magma cools and crystallizes, either on the surface or in shallow underground chambers. Individual lava flows may extend for 10 to 20 kilometers or 6 to 12 miles from their source vents, cooling to form rough, blocky surfaces called aa, or smooth, ropey surfaces called pahoehoe. Depending on the flow rate, gas content, and cooling conditions, these lava fields create harsh landscapes initially devoid of soil or vegetation, requiring hundreds to thousands of years for pioneer plant species to establish themselves in cracks and crevices where wind-blown dust and organic matter gradually accumulate. The age progression visible across the Galápagos archipelago demonstrates the gradual process of ecological succession on volcanic islands, from the barren lava fields of recent eruptions to the diverse plant communities that develop over thousands of years on older, more weathered volcanic soils. The youngest lava flows, appearing as black, glassy surfaces with minimal vegetation, may receive their first plant colonists within months or years of cooling. As seeds carried by wind, ocean currents, or migrating birds find tiny pockets of accumulated soil in rock crevices, pioneer species such as lava cactus and malugo can survive on these harsh surfaces with minimal soil and water, gradually modifying local conditions through their growth and decomposition to create habitat for additional species. The process of soil formation on volcanic islands proceeds slowly through the gradual weathering of basaltic rock, which breaks down under the influence of rain, temperature fluctuations, and organic acids produced by plant roots and decomposing vegetation in the humid highlands of larger islands, where annual rainfall may exceed 1,500 millimeters or 59 inches. Soil development occurs more rapidly than in the arid lowlands, where precipitation may be less than 200 millimeters or 8 inches per year. The red and brown soils that characterize many areas of the older islands contain clay minerals formed by the chemical weathering of volcanic glass and feldspar crystals, creating relatively fertile substrates that support increasingly diverse plant communities. As we mentally traverse these volcanic landscapes shaped by fire and time, perhaps you might reflect on what draws you to such dramatic yet peaceful island environments. What aspects of volcanic landscapes bring you a sense of tranquility despite their explosive origins? If you feel moved to share such thoughts in the comments below, many would find comfort in reading about the dramatic places that somehow soothe our restless minds. The climate patterns across the Galápagos Islands reflect their equatorial position and the influence of several major ocean currents that converge in this region, creating distinct wet and dry seasons despite the minimal seasonal variation in day length and solar radiation. The cool Humboldt Current, flowing northward along the western coast of South America, brings nutrient-rich waters that support abundant marine life while moderating air temperatures throughout much of the year. Surface water temperatures typically range from 18 to 24 degrees Celsius, or 64 to 75 degrees Fahrenheit during the cool season from June through November, rising to 24 to 28 degrees Celsius, or 75 to 82 degrees Fahrenheit during the warm season from December through May. The warm season coincides with the arrival of the Panama Current, which brings warmer waters and increased rainfall to the islands, transforming the brown, drought-stressed landscapes of the dry season into green expanses of rapidly growing vegetation. During El Niño years, when warm water temperatures persist longer than usual, rainfall may increase dramatically, sometimes exceeding 3,000 millimeters or 118 inches annually compared to normal years, when some areas receive less than 250 millimeters or 10 inches. These extreme precipitation events can trigger massive plant growth and reproduction, creating temporary abundance that supports population booms among many animal species. The trade winds that blow consistently from the southeast create distinct microclimates across individual islands, with windward slopes receiving significantly more rainfall than leeward areas. The orographic lifting of moisture-laden air as it encounters volcanic peaks creates precipitation patterns that may vary by more than 1,000 millimeters or 39 inches annually between locations separated by only a few kilometers. The highest elevations on larger islands may be shrouded in mist and clouds for much of the year, creating humid conditions that support unique plant communities, including the endemic Scalesia forests found nowhere else on Earth. The isolation of the Galápagos Islands, located more than 1,000 kilometers or 620 miles from the nearest continental landmass, has created one of the world's most remarkable examples of adaptive radiation, where small numbers of colonizing species have evolved into multiple endemic forms adapted to different island environments. The island's geological youth, with with the oldest surfaces dating back only 3 to 4 million years, means that all current plant and animal populations must have arrived through long-distance dispersal events that occurred after the islands formed, creating natural experiments in evolution and biogeography. The famous Darwin's finches represent perhaps the best-known example of adaptive radiation in the Galápagos, with 18 species that evolved from a single ancestral population that probably arrived from mainland South America 2 to 3 million years ago. These birds have diversified to occupy virtually every available ecological niche on the islands, from ground-dwelling seed-eaters with massive beaks capable of cracking large, hard seeds, to tree-dwelling insectivores with delicate beaks adapted for probing bark crevices and flower heads. The largest ground finch possesses a beak measuring up to 20 millimeters, or 0.8 inches in depth, while the warbler finch has a needle-like beak only 8 millimeters, or 0.3 inches long, demonstrating the remarkable morphological diversity that can evolve within a single lineage over relatively short geological time periods. The giant tortoises that give the islands their name derived from the Spanish Galapago, meaning saddle after the shape of certain tortoise shells, represent another remarkable example of island evolution. These massive reptiles, weighing up to 250 kilograms or 550 pounds, and living for more than 100 years, evolved from smaller mainland ancestors that probably arrived by floating across the ocean currents 2 to 3 million years ago. Different islands support distinct subspecies of giant tortoises, each adapted to local food sources and environmental conditions, with shell shapes ranging from domed forms on islands with abundant low-growing vegetation to saddleback shapes that allow access to higher browse on islands with tall cacti and shrubs. The marine iguanas of the Galápagos represent the world's only truly marine lizards, having evolved from terrestrial ancestors to become specialized feeders on marine algae that grow on underwater rocks and coral surfaces. These remarkable reptiles can dive to depths exceeding 25 meters or 82 feet and remain submerged for more than 30 minutes while foraging, using their flattened tails for propulsion and their sharp claws for gripping slippery rocks in heavy surf. The physiological adaptations that allow marine iguanas to survive in saltwater include specialized salt glands that concentrate and excrete excess sodium through nasal secretions, creating the distinctive white salt crystals often visible around their nostrils. The endemic species of the Galápagos demonstrate varying degrees of evolutionary divergence from their mainland relatives, with some groups showing dramatic morphological and ecological changes, while others remain relatively similar to ancestral forms. The Galápagos hawks, for example, show only minor differences from mainland relatives despite thousands of years of isolation, while the flightless cormorants have lost the ability to fly entirely, evolving vestigial wings that are useless for flight, but retained for balance and display purposes. This variation in evolutionary rates reflects differences in selective pressures, population sizes, and genetic characteristics that influence how rapidly species change in isolated environments. The plant communities of the Galápagos show equally dramatic patterns of endemism and adaptive radiation, with approximately 40% of native plant species found nowhere else on Earth. The endemic prickly pear cacti have evolved into tree-like forms on islands where giant tortoises are present, developing thick, bark-like stems and elevated growing points that place their paths beyond the reach of browsing reptiles. On islands without tortoises, the same cactus species maintain the low, spreading growth forms typical of their mainland relatives, demonstrating how the presence or absence of specific herbivores can drive evolutionary changes in plant architecture. Perhaps you have experienced peaceful moments in natural settings where you could observe the slow rhythms of wildlife and plant growth that remind you of the gradual processes we explore on these volcanic islands. If you feel inclined to share such experiences in the comments, others would find comfort in reading about the natural places that have provided you with tranquil observation of life's patterns. The ocean currents that surround the Galápagos Islands create one of the most diverse marine ecosystems in the tropical Pacific, supporting species typically found in cold, temperate waters, alongside tropical coral reef communities. The Cromwell Current, an equatorial undercurrent flowing eastward at depths of 50 to 400 meters, or 164 to 1,310 feet, brings cold, nutrient-rich water to the surface when it encounters the underwater slopes of the Galápagos platform. This upwelling creates highly productive waters that support massive populations of phytoplankton, which form the base of food webs extending from tiny zooplankton to blue whales. The marine productivity around the Galápagos supports approximately 2,900 marine species, including 25% endemics found nowhere else on Earth. The waters around the islands serve as feeding and breeding grounds for numerous migratory species, including humpback whales that travel more than 8,000 kilometers or 5,000 miles from feeding areas near Antarctica, and green sea turtles that nest on Galápagos beaches after journeys of thousands of kilometers across the Pacific Ocean. The predictable abundance of marine life has allowed the evolution of unique behaviors, such as the tool use displayed by some finch species that employ cactus spines to extract insects from tree bark. The underwater topography around the Galápagos Islands reflects their volcanic origins, with steep submarine slopes dropping rapidly from shallow coastal waters to abyssal depths exceeding 3,000 meters or 9,840 feet. The shallow waters around many islands, extending to depths of 20 to 50 meters or 66 to 164 feet, support coral communities despite the periodic cooling caused by upwelling currents. These coral reefs show lower diversity than typical tropical reefs due to the challenging environmental conditions, but they support unique assemblages of fish species adapted to the variable temperature and nutrient conditions characteristic of Galápagos waters. The Galápagos Spreading Center, located approximately 200 kilometers or 124 miles north of the islands, represents an active mid-ocean ridge where new oceanic crust is being created through volcanic activity. This underwater mountain range generates hydrothermal vents that support chemosynthetic communities based on bacteria that derive energy from chemical reactions rather than photosynthesis, creating oases of life in the deep ocean that operate independently of solar energy. The discovery of these deep-sea communities around the Galápagos in the 1970s revolutionized understanding of life's potential in extreme environments and contributed to theories about the origins of life on Earth. The geological processes that continue to shape the Galápagos Islands operate on timescales ranging from hours to millions of years. From the rapid cooling of individual lava flows to the gradual subsidence and erosion that will eventually eliminate older islands entirely. The most recent major eruption occurred on Fernandina Island in 2020, adding new land to the youngest and most volcanically active island in the archipelago. Such eruptions typically involve the effusion of fluid basaltic lava that flows downslope at rates of several meters per hour, creating new land surface while destroying existing vegetation and temporarily altering local ecosystems. The erosional processes that gradually wear down volcanic islands become increasingly important as volcanic activity wanes with distance from the hotspot. Wave action along exposed coastlines creates sea cliffs that may retreat several centimeters per year, while chemical weathering in humid highland areas breaks down volcanic rocks into clay-rich soils at rates of millimeters per century. The balance between volcanic construction and erosional destruction determines the ultimate lifespan of individual islands, with older eastern islands showing clear signs of subsidence and erosion that will eventually reduce them to seamounts below sea level. The human history of the Galápagos Islands spans less than 500 years, beginning with their accidental discovery by Spanish Bishop Tomás de Berlanga in 1535 during a voyage from Panama to Peru. The islands remained uninhabited by permanent human populations until the 19th century, though they served as bases for pirates, whalers, and other maritime visitors who often introduced non-native species that dramatically altered island ecosystems. The arrival of goats, pigs, cats, and rats created new ecological pressures that drove several native species to extinction and continue to challenge conservation efforts today. The scientific significance of the Galápagos Islands was first recognized by Charles Darwin during his 1835 visit aboard HMS Beagle, when his observations of endemic species and their relationships to mainland forms contributed to his development of the theory of evolution by natural selection. Darwin spent only 5 weeks in the islands, yet his careful observations of finches, tortoises, and marine iguanas provided crucial evidence for understanding how species change over time in response to environmental pressures. The islands became a UNESCO World Heritage Site in 1978, recognizing their outstanding universal value for understanding evolutionary processes. The current human population of approximately 25,000 people is concentrated on 4 inhabited islands, with strict controls on immigration and development, designed to minimize human impacts on the fragile island ecosystems. Tourism, carefully managed through permits and guides, provides the primary economic activity, while supporting conservation efforts through entry fees and visitor spending. The challenge of balancing human needs with ecosystem protection continues to evolve as global climate change and increasing connectivity with the mainland create new pressures on these remarkable islands. The research stations established throughout the archipelago continue to provide insights into evolutionary processes, climate change impacts, and conservation strategies that extend far beyond the Galápagos themselves. Long-term studies of finch populations have documented evolutionary changes occurring over periods of just a few years in response to climatic variations, providing real-time observations of natural selection in action. These studies demonstrate that evolution is not just a historical process, but an ongoing response to environmental change that continues to shape life on these volcanic islands. As our mental voyage among these evolutionary laboratories begins to draw toward its conclusion, perhaps you might reflect on which aspects of these unique island ecosystems you find most conducive to peaceful relaxation. If you feel moved to share such observations in the comments below, many listeners find that reading about what brings others peaceful sleep helps enhance their own rest. The daily rhythms that characterize life on the Galápagos Islands follow patterns established over millions of years of evolution, from the precise timing of seabird nesting cycles to the seasonal migrations of marine mammals that traverse thousands of kilometers of open ocean. The equatorial position of the islands creates remarkably consistent day-night cycles throughout the year, with sunrise and sunset times varying by less than 30 minutes between summer and winter solstices. This consistency provides stable environmental cues that allow the precise coordination of biological activities across species and ecosystems. The breeding cycles of Galápagos wildlife demonstrate remarkable adaptations to local environmental conditions, with many species timing reproduction to coincide with periods of optimal food availability or favorable weather conditions. The waved albatrosses that nest exclusively on Hispaniola Island synchronize their breeding so perfectly that nearly all eggs are laid within a 2-week period each April, allowing parents to exploit predictable wind patterns for efficient foraging flights that may extend for thousands of kilometers across the southeastern Pacific. The seasonal movements of nutrients through Galápagos ecosystems reflect the complex interactions between ocean currents, weather patterns, and biological processes that operate at multiple scales, from local food webs to ocean basin circulation. The upwelling of deep, cold water during certain seasons brings nutrients from ocean depths to surface waters, where they support phytoplankton blooms that propagate up through food webs to support massive populations of seabirds, marine mammals, and fish. These pulses of productivity create periods of abundance that many species have evolved to exploit through precisely timed migrations and breeding cycles. The volcanic soils of the Galápagos Islands provide natural laboratories for studying plant succession and ecosystem development in the absence of human disturbance, revealing how biological communities assemble and change over time on newly created substrates. The youngest lava flows show predictable patterns of colonization, beginning with pioneer species capable of surviving in harsh conditions with minimal soil and water, followed by successional stages that gradually increase in diversity and structural complexity as soil development and microclimate modification create habitat for additional species. The isolation of individual islands within the archipelago has created numerous opportunities for allopatric speciation, where populations separated by water barriers evolve independently until they become distinct species. The mockingbirds of the Galápagos demonstrate this process clearly, with 4 species distributed among different islands or island groups, each showing adaptations to local food sources and environmental conditions. The Florina mockingbird, now extinct on its original island due to habitat destruction, survives only on 2 small satellite islets where it maintains populations of fewer than 100 individuals. The genetic studies of Galápagos organisms reveal patterns of colonization, adaptation, and speciation that provide insights into fundamental evolutionary processes operating across all life forms. DNA analyses of giant tortoises have revealed multiple colonization events from mainland South America, with different lineages establishing populations on different islands and subsequently evolving distinct characteristics in isolation. Similar patterns appear in other groups, suggesting that the islands have been colonized repeatedly by multiple waves of immigrants that arrived at different times and under different environmental conditions. The conservation challenges facing the Galápagos Islands reflect global issues of biodiversity protection, climate change adaptation, and sustainable development that affect isolated ecosystems worldwide. The introduction of non-native species continues to pose serious threats to endemic organisms, while climate change affects ocean temperatures and precipitation patterns that may alter the environmental conditions to which native species are adapted. Rising sea levels threaten low-lying nesting beaches used by sea turtles and seabirds, while ocean acidification may affect the coral communities and other marine calcifying organisms. The ongoing volcanic activity that continues to build the Galápagos Islands provides a reminder that these ecosystems exist in a state of constant geological flux, where new land surfaces are created while older areas are gradually eroded away by wave action and weathering. This dynamic geological setting creates continuous opportunities for evolutionary innovation, while also ensuring that no species or ecosystem can remain unchanged indefinitely. The balance between creation and destruction that characterizes volcanic island systems provides a powerful metaphor for the dynamic nature of all ecological processes. The interconnectedness of terrestrial and marine ecosystems around the Galápagos Islands demonstrates the artificial nature of boundaries between different environmental realms, where nutrients cycle between land and sea through the activities of seabirds that feed in the ocean and deposit guano on terrestrial vegetation. The marine iguanas that graze on intertidal algae provide another example of these connections, concentrating marine productivity in terrestrial ecosystems through their foraging activities in coastal waters. As our exploration of these remarkable islands draws to its close, we return to the fundamental recognition that the Galápagos represent a living laboratory where the processes of evolution, adaptation, and extinction continue to operate with the same mechanisms that have shaped life on Earth for billions of years. The volcanic forces that built these islands from the ocean floor continue to operate today, adding new land while older surfaces are gradually weathered and eroded by rain, wind, and waves. The biological communities that inhabit these dynamic landscapes change continuously as species respond to environmental variations, competitive interactions, and genetic changes that accumulate over generations. The timeless cycles of day and night, of wet and dry seasons, of volcanic construction and erosion continue with the same patterns that have characterized these islands since their formation millions of years ago. The trade winds that bring moisture from the vast Pacific Ocean blow with the same consistency that has shaped vegetation patterns for thousands of years, while ocean currents follow paths established by the Earth's rotation and the topography of ocean basins. The biological rhythms of reproduction, migration, and seasonal activity reflect adaptations to these environmental patterns that have been refined through countless generations of natural selection. In this realm, where evolution can be observed in real time, where volcanic landscapes record the Earth's internal processes, and where isolation has created unique forms of life found nowhere else on our planet. We find a landscape that invites contemplation of change and continuity across vast timescales. The giant tortoises that move slowly across ancient lava fields carry genetic lineages that stretch back millions of years. Their patient progress, reflecting the gradual pace of evolutionary change that connects the present moment with the deep history of life on Earth. The waves that crash against volcanic shorelines continue the gradual work of erosion that will eventually return these islands to the sea from which they rose, completing cycles of creation and destruction that operate on timescales beyond human comprehension, yet follow physical laws as predictable as the sunrise. The lava that cools and hardens on recent flows will gradually develop cracks where pioneer plants will establish themselves, beginning new cycles of ecological succession that will unfold over centuries and millennia. As consciousness fades into the peaceful realm of sleep, imagine yourself sitting quietly on a weathered lava flow, overlooking the Pacific Ocean in the soft light of early evening, watching frigate birds glide effortlessly on thermal currents rising from sun-warmed volcanic rock, while listening to the distant barking of sea lions on beaches where marine iguanas bask motionlessly in the fading warmth. The volcanic landscape stretches toward the horizon with the timeless patience of geological processes, its rough textures softened by the golden light, while the ocean beyond reflects the first stars appearing in the equatorial sky. And if this journey across these evolutionary islands has brought you closer to the peaceful sleep you seek, remember to subscribe to join us on future explorations of our planet's most remote yet magnificent landscapes, where the patient processes of creation and change invite rest and renewal far from the urgency of daily concerns.